Warm greetings to you all this day. In 4.5, which we're covering today, we're going to be solving quadratic equations by finding square roots, which is a mouthful, but mostly it means we're going to use square roots instead of factoring. This only works for some of our equations, but in order to be able to do it, we are going to have to talk about square roots first, because it's probably been a while since you dealt with those. So the first thing we're going to talk about today is simplifying square roots. Hopefully this will be somewhat review, although I'm going to explain it all in case you don't remember. Then we're going to talk about rationalizing the denominator, which is actually part of simplifying square roots. But it's a pretty big thing, so I'm listing it as a separate item so we'll remember. And then we're going to use our square roots to solve equations. I should point out that the equations we can solve with square roots today are ones where b is 0. That is, there's an x squared term, but there's no term with just x in it. And those ones we can solve using square roots. They can be a little easier than factoring. So we're going to try that today. When we get our solutions, we're going to have to simplify them because they'll have square roots in them. So stepping right in here to simplifying square roots, one of the important things to remember about square roots is that you can combine them or separate them over multiplication. That's multiplication only, not over addition. To show you what I mean, 36 is the product of 9 and 4. So we can split the square root of 36 into the square root of 9 times the square root of 4. But we cannot split, for example, the square root of 25 into the square root of 16 and the square root of 9 by addition. Notice 16 plus 9 would be 25. But if we add these ones up, square root of 25 is 5, but the square root of 16 is 4, and the square root of 9 is 3. That would be 7 on this side. These are not the same. Whereas if you look here with the multiplication, the square root of 36 is 6, the square root of 9 is 3, and the square root of 4 is 2. So these are equal. This is 6 equals 6. So we can split a square root up over multiplication, but not over addition. And that changes the way we're going to approach things, or it determines the way we're going to approach things when we simplify square roots. Now, these square roots simplify very nicely by themselves because the square root of 36 is 6. We know them already. But I should point out, if you get a problem where you have two square roots multiplied together, you can go ahead and combine them as well. Like I said, combined or separated. So the square root of 12 times the square root of 3 is the same as the square root of 36, which is, of course, 6. A lot of times when we're simplifying square roots, what we mean by that is that the inside is not a perfect square, so we can't just get a nice answer. For example, the square root of 75, it's somewhere between 8, which would be 8 squared would be 64, and 9, for which the square would be 81. It's somewhere in between those two. But we don't do decimal approximations because Mr. Barnard doesn't like them. So we're going to simplify this square root by breaking it down into its pieces by multiplication. Probably when you look at 75, the first factors you're going to think of are going to be 25 and 3, just because you're used to dealing with quarters with money. But as soon as you split this into 25 times 3, you should note the square root of 25 is a nice number. 25 is a perfect square. So the square root of 25 is just 5. Now the square root of 3 we can't break down. 3 is prime and not thus a perfect square. So we just leave it like this. This is a simplified square root, 5 times the square root of 3. So we look for the perfect square factors, and we find the square root of them, and anything that's left behind just stays inside the square root. And that's the whole trick behind simplifying square roots. Everything else is just a different version of doing this. Now, if you didn't see that this was 25 times 3, you might actually have split it up as 15 times 5, which is perfectly fine. Notice we don't see any squares here, so just keep going. Now 5 is prime, but 15 is 5 times 3. And you'll note that if you split this up far enough, you'll find the two that are the same. And notice if we put those together, we'd get the square root of 25. You don't actually have to multiply them, because if you have two that are the same, just put them together and cancel out the square root. So that just becomes 5. Square root of 5 times the square root of 5 is 5. And then the square root of 3 is the one that's all by itself. So if you find a pair of square roots, you can cancel out the square roots, and the ones that are left by themselves have to stay. Let's do another example. The square root of 126, that's a big number, so you can start breaking it down. The easiest way to start is to note that it's even, so we can divide it by 2. In fact, 2 times 63 is 126. 2 is not a perfect square, nor is 63. So we break 63 down. I note both of those numbers are divisible by 3. So I'm going to divide by 3. That gives me 21, which is a number I recognize. This is 3 times 7. So looking at this, the 2 3's I have here are right there. So I can combine that into just a regular 3. But the square root of 2 and the square root of 7 don't have any pairs. So 2 times 7 is 14. The 14 has to stay in the square root. One last example, the square root of 80. I actually, if you think about this long enough, if you're sharp, you'll realize that's 16 times 5, and you can just do the square root of 16 is 4, so 4 square roots of 5. But if you're like me, you may start splitting it up just with whatever numbers you find. Notice 80 is 4 times 20, so that's a perfect square there. That's going to be 2. But the 20s breaks that down into the square root of 4 times 5. So that's 2 times 2 is 4, or if you note they're the same, the square roots cancel. Any way that you split this up, then you're going to get 4 times the square root of 5. So that's simplifying square roots that don't have fractions. When we start simplifying square roots with fractions, we have an extra step, because the denominator is not allowed to have a square root in it. And that's why we call it rationalizing. Rational numbers do not include square roots. We need the denominator of our fractions to not have square roots in it. Sometimes that works out very nicely. For example, this fraction, the square root of 11 over 144, division is just a fancy type of multiplication, so we can split this square root up over the fraction. Now the top is square root of 11 is not going to simplify, but the square root of 144, we know it's just 12. So that's nice. The denominator rationalized itself just because the bottom was a perfect square. Won't always be that nice. For example, the square root of 2/15, when we split that up, the square root of 2 and the square root of 15, neither one of those is a perfect square. But we're not allowed to leave the square root of 15 down here in the denominator. We are going to have to, in fact, get rid of it. And the best way, perhaps the only way, it's the only way I know, to get rid of the square root of 15 down here is to multiply by itself, the square root of 15. But since this is a fraction, whatever we multiply on the bottom, we have to multiply on the top as well to keep the fraction the same. Now the square root of 15 times the square root of 15 is going to be 15, and the square root of 2 times the square root of 15 is the square root of 30. So here notice that the bottom has been rationalized, although it comes at a cost. So the number on the top gets bigger, but we'll just have to deal with that. The bottom is rationalized, and that's the important part. You are not allowed to leave radicals, square roots, on the bottom of your fractions. Unfortunately, occasionally you'll see actually a sum on the bottom that includes a square root. Rationalizing is a little trickier. Your instinctive response may be to multiply by the square root of 2. The problem is it's not actually going to work, because when we distribute that square root of 2, we wind up with 5 square roots of 2 minus 2. Not the square root didn't go away, it's still there, it's over by the 5. And if we multiply by it again, the square root will move back over here. So we're going to have to take a different approach. In fact, what you do is you try to produce a difference of squares. Remember that was a minus b times a plus b. So if this is minus, you're going to multiply by a plus version, and if it's already plus, you'll multiply by a minus version. This is called the conjugate of 5 minus the square root of 2. The conjugate is 5 plus the square root of 2. It's the same values, but with the opposite sign. What that actually does is produces the difference of squares. The square roots are going to cancel, and that's what we like. Now on the top, you just distribute the 4, so we get 20 plus 4 square roots of 5. On the bottom, we'll have to FOIL. Notice the first term is 25. Right? The outside and inside make 5 square roots of 2 and negative 5 square roots of 2. And the last two terms multiply to be just negative 2. That's notice the square root of 2 times the square root of 2 is 2. Now these outers and inners are going to cancel, right? 5 square roots of 2 minus 5 square roots of 2, which leaves just 25 minus 2 is 23. So notice that bottom, the denominator is rationalized, although the top got more complicated. That's to be expected. Let's do one more. Notice this one has 7 plus the square root of 5, so its conjugate is 7 minus the square root of 5, and I multiply that on top and bottom. On the top I distribute, I get negative 42 plus 6 square roots of 5. On the bottom, that's 49 minus 5. Notice I didn't even bother writing the middle two terms. I know they're going to cancel. I'm going to ignore them. So 49 minus this 5 is 44. Now in this case, you may or may not have noticed, but each of the coefficients, each of the numbers here is even, so I can divide them all by 2. That gives me 21, 3, and 22. So this is actually the simplest version of this square root problem. Notice the bottom is rationalized, which is the important part. I also reduced. That was a lot, but the point of learning how to deal with square roots is so that we can solve equations, and that's the last thing we're going to try today. Here's an example of an equation. Notice, as I said earlier, b is missing. That is, there's no x term. If there is an x term, we're not going to be able to use square roots until we learn to complete squares, which is next, 4.6. So for today, all the problems you're going to see that are equations to solve, the x term will be missing. Here, instead of trying to get everything equal to 0, because there's no x term, what we can do is we can isolate the x squared. So we want to solve for the x squared, get it all by itself. So we're going to start by adding 15, just like we would if it were a regular x. We're going to add 15, which makes 80. And then we're going to divide the 2. So x squared equals 40. And you cancel out the square by doing the square root of both sides. And that's going to give you x equals the square root of 40. Anytime you square root an x squared, though, you need to account for both the positive and negative square roots. Because remember, if you square a negative number, it becomes positive. So there's actually 2 different values that you can square to get positive 40. One of them's positive and one of them's negative. So I get plus or minus the square root of 40. This right here is not a nice answer, like it's not a whole number, but I can simplify it because 40 is 4 times 10, and 4 is square. So the square root of 4 is 2, and then the 10 has to stay behind. So plus or minus 2 square roots of 10. And that's my solution. Notice with a plus or minus, that's 2 solutions. One that's the positive 2 square roots of 10, and one that's negative 2 square roots of 10. And those are my 2 answers. In a slightly more complicated example, where the x minus 4 is all inside the square with the parentheses, it's basically the same, but remember you got to isolate the square first. So in this case I'm going to multiply by 3. And now before I add the 4, I have to get rid of the square because the 4 is on the inside. So I take the square root of both sides now. That gives me x minus 4 equals plus or minus the square root of 33. To get the x by itself as my last step, I'm going to add 4. Since I know the sign on the 4, I'm going to put it in front of my plus or minus. That gives me x equals positive 4 plus or minus the square root of 33. Again, that's 2 answers, 4 plus the square root of 33 and 4 minus the square root of 33. But that gives me my solutions to the original equation. So that's solving equations. That's actually the entire lesson. It's a pretty short lesson today. But remember what we talked about was simplifying square roots. We break them up, right, and look for the perfect squares. Rationalizing the denominator, which you do by multiplying on top and bottom to get rid of the square root on the bottom. Solving equations by